We're going to finish up our discussion of hypothesis testing in Chapter 9 by just touching on the topic of testing the difference between two means. When we were in Chapter 8 and we tested means and we tested proportions, that's only one type of hypothesis test. There's actually lots of other hypothesis tests that can be done, and we're going to just touch on one other type so that you can see that there's other ways to use a hypothesis test. So in this chapter, we're going to be looking at testing the difference between two means using the z-test. You may see on your test a problem where you need to test the difference between two means using the t-test, but it's the exact same difference between these two types of tests as it was in Chapter 8. So on your homework, you're only going to see problems using the z-test. But I believe in the review problem that I have in D2L and then also again on the final, you could see a t-test. So what does it mean by testing the difference between two means? Oh, and let me mention also that remember that these slides that we have are from the 7th edition book, because I like them a lot better than the 8th edition slides. And so it actually shows here 9.1 and 9.2, but 9.1 in the old edition book actually covers 9.1 and 9.2 in the new edition. So we're only going to cover really 9.1, but that's in your homework, that's 9.1 and 9.2. Because in the new edition book, in the 8th edition book, 9.1 is actually like an intro to testing the difference between two means, proportions, or variances, and 9.2 is testing the difference between two means. So in the new edition book, this is 9.2 and 9.1 is just like an intro. So back to the discussion of what does this mean to test the difference between two means. Well, what we're talking about is you have two samples, and with those two samples, each of the samples would have their own mean. The samples that you collect have to be independent of each other. So, for instance, let's say you were sampling students. You might pick one sample of students from one high school and another sample of students from another high school. Or you may pick one sample of students from one community college and another sample of students from another community college. But you want them to be independent. And so you don't want there to be a chance of an overlap or anything. The standard deviations of both populations must be known if we're going to use a z-test. Of course, if we don't know the population standard deviation, we can still do this. We just have to use a t-test and do the degrees of freedom. This is the formula that we're going to be using. I'm not really going to talk about it right this minute because it doesn't really make a lot of sense what we're doing with this new z formula until we see what we're trying to look at. So I'm going to go to this next slide and talk about what we're trying to compare. So if you take two different samples, and again, these samples are supposed to be independent of each other, and you want to compare these two samples. You want to see, here's my average I have for sample 1, here's my average I have from sample 2. And what we're trying to decide is whether or not the difference is not significant between those two samples, or whether the difference is significant between the two samples. If the difference is not significant between the two samples, then that means that the two samples could have been selected from the same population. So I'm going to use the high school example. So basically what we're saying is I've selected sample 1 from high school A, and I've selected sample 2 from high school B, but I find that these two samples are really very, very similar. then I can really just say that these two high schools could be thought of as one population, that they're really, even though they weren't the same, we could think of them as coming from the same population, so that those two high schools are essentially all from one large population. Thus, the samples that we picked from one really were the same as the samples we picked from the other. The other thing, and this is when we would reject the null hypothesis, is that those two high schools were so different that we got different samples from them, meaning that, you know, these two were not alike. Thus, high school A and high school B can't really be considered as part of the same population. They have to be considered as two separate populations. So that's what we're trying to decide. We're trying to decide is where we got these samples from. Are they so similar that you could just think of them as one cohesive population, or do I literally have to think of them as being two different populations that are different from each other? And so our null hypothesis is going to be that our null hypothesis here is going to be that the mean from sample 1 is the same as the mean from sample 2. And then the alternative hypothesis that we're going to have is going to be either that mean 1 is larger than, smaller than, or not equal to mean 2. So the two groups are different from each other, or mean 1 is larger than mean 2, or mean 1 is smaller than mean 2, making the population that they were taken from, or the two populations that they were taken from, different from each other. So as you know, with these hypothesis tests, it's a lot easier to just see an example of them rather than to talk about them in generalities at length. So let's go back and look at this formula that we had. So if you recall, we have two means now. And so because we have two means, we have the two sample means and we have the two population means, and we take the difference of those. Then we also have two population standard deviations and potentially two different size samples. The two groups that you sample, or the two samples that you take, don't have to be the same size. So you have an N1 and an N2. So this is what a problem might look like. This one says a study using two random samples of 35 people each. So in this case, 35 people each. They are the same size. And so this would mean N1, let me get that a little smaller. N1 is 35 and N2 is also 35. And in the age group of 26 to 35 years, I'm going to just call this the younger group, because I think that listing the age ranges makes it just confusing, too many numbers. So in the younger group, each week on leisure activities, they spent 39.6 hours. So that is the average from the first group. So the younger group, we'll call that X1. Their average was 39.6. And then it says, and those in the age group 46 to 55, we'll just call that the older group. So the older group spent 35.4 hours. So the second group average was 35.4. Of course, this is hours because it's how much time they spent on leisure. Assume that the population standard deviation for those in the first group found by previous studies is 6.3, and the population standard deviation of those in the second group was 5.8. So they're telling us specifically, again, that this is the population standard deviation. So this is the sigma. So sigma 1 is 6.3, and sigma 2 is 5.8. And it's a sigma because it's from the population. If it was from the sample, it'd be an S. And then they list our alpha is 0.05. And can it be concluded that there's a significant difference? Remember, difference, they didn't say larger or smaller, it says different, so we're just talking about a not equals. So we'll state the original hypothesis. As I said, you're always going to have the null hypothesis is going to be that the average of the two samples, or the mean of the two groups, is the same. So our null hypothesis is that mean 1 equals mean 2. Our alternative hypothesis is that, because it says difference, that mean 1 does not equal mean 2. If we look for the critical values, let me pull the chart up here. So we have our table here, and it says that our alpha is 0.05. Oop, I lost my table, just a second. It says our alpha is 0.05, and we had a z-test. So we're going to look at, let me point out a couple things here. So because it's a not equals, that means that it's two tails, of course. So two-tailed. And then the alpha is 0.05. So we're looking at a two-tail z-test, because we have the sigmas. It's a z-test. It's two tails, and our alpha is 0.05. So that's what we're looking for on the chart. So two tails, 0.05, and then a z-test is all the way at the bottom, because we don't have to worry about degrees of freedom when we have the population standard deviation. So this is where we get the 1.960. Okay, so right here. I don't think I can draw on this. I can highlight it. So that gives us this 1.96. So if I put that in my work here, I like to do that with the picture. So we're going to have our two tails be negative 1.96 and positive 1.96. And we're going to reject if we end up with our test value either below 1.96 or above 1.96 in the dark area. Okay? So we're going to reject if we're here, or reject if we're here. If we're in the shaded areas, we will reject. So now to compute this, I'm going to use this formula, and I'll fill all these things in fresh so you can see where they all came from. So our z is going to be x sub 1 minus x sub 2. Remember, that was 39.6 hours for the younger group and 35.4 hours for the older group. So 39.6 minus 35.4. And then we're going to subtract mu1 minus mu2. But remember, our assumption is that mu1 and mu2 are equal to each other. Well, if mu1 and mu2 are equal to each other, it doesn't matter what they are. If I subtract them, it's going to be 0. And so even though this formula looks really long, this part of the formula actually just kind of falls out, because mu1 minus mu2 is just 0. So I don't really have to worry about that part. And that happens every time in these problems. You'll always get a 0, because our assumption, our null hypothesis, is always going to be that the two means are the same. Then we're going to do the square root of the population standard deviation for the first group, and the population standard deviation for the second group are going to be on top. So that's 6.3 and 5.8. And that was the standard deviation, so we still need to square it. If by chance they gave us variance, you wouldn't have to square it, but they don't typically do that. They usually just give us standard deviation. And then in this case, it said both groups were 35. Both samples were 35. So our N1 and our N2 are both 35. If we compute that, the top comes out to be 4.2. The square root of the bottom comes out to be 1.447. You can take the time to actually calculate that if you want. Again, I would do this calculation. So I would do 6.3 squared divided by 35 plus 5.8 squared divided by 35. Hit equals and then do the square root of it. I think that's the safest. That way you don't end up with your parentheses in the wrong place. And then this comes out to be about 2.90. So where is 2.90? Well, 2.90 is up here. It's above 1.96, so it would be up in this area. Well, that's the rejection region. So what we're going to do is our decision is going to be that we reject the null hypothesis because, and they say it a little bit more formally, as you know, all you have to say is that because we're in the critical region. So reject the null hypothesis because we're in the critical region. 2.9 is in the critical region, and so there is enough evidence to support the claim that the means are not equal. That is, the average of the time spent on leisure activities is different for the groups. In other words, the two groups really are different. It's not like they're one big population. It's like they're really two separate populations. There's a younger population and there's an older population, and they're not similar enough to think of them as all one population. So there's enough evidence to support the claim that the means are not equal or that the groups are different from each other. So in our next example, we're looking at college sports. And with this example, they happen to give the raw data. But I'm not going to do that in your problems any more than I did in Chapter 8. And in fact, my preferred way, this is from one of the homework assignments in Connect Math, I like to give it in a table. After it's given in words, I like to just give in a table what the x bar is, the sigma, and the n. So in this case, if you think of this is like group 1, this would be like your x bar 1 and your x bar 2. And then this would be like your sigma 1 and your sigma 2 and your n1 and your n2. Again, this is a different example. This is one from your homework. But I just wanted to show you that on the exam, I will probably give you like a summary table like this so that you can kind of keep track of it, because I know there's a lot to pick out of these problems. And I definitely will not give you raw data. So let me get rid of this problem since this isn't part of what we're doing. Okay. So in this case, it says a researcher hypothesizes that the average number of sports that colleges offer for males is greater than the average number of sports that colleges offer for females. This is probably all based on the federal regulation of Title IX, if you're familiar with that. So it says a sample of the number of sports offered by colleges is shown. At alpha equals 0.10, is there enough evidence to support the claim? So as you can tell, there's, what is that, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 50 in this sample, and there's also 50 in this sample. Now I want to point something out. Just because we're sampling from colleges, we don't want, these 50 would not necessarily be from the same colleges as these 50. This would be random. So you would randomly sample 50 colleges and count their males. Then you would randomly sample 50 colleges and count their females, their sports for the females and their sports for the males. But you would not just say, I'm going to sample 50 colleges and count the male and female at those colleges. Those would not be independent samples. So to keep these independent, you would literally do a sample of 50 for the males, and then you would do a completely new sample of 50 and look at their females' sports. So in this case, it says we're going to have the alpha is 0.10, and they want to know, is there enough evidence to support the claim? And remember that the claim is that males is greater. The number of sports for males is greater. So as you can see here, we have a null hypothesis that mu1 equals mu2. That is always, for these problems where we're comparing two means, we're always going to have those equal. The alternative hypothesis is going to be that mu1 is greater than mu2, because mu1 is the males. We'll consider this group 1. And we'll consider the females group 2. Just because that's the order they gave them in, it's a lot easier than trying to flip them around and keep track. So we're going to cheat a little bit because, again, we're not going to have raw data, and let them calculate for us that the x bar 1 is 8.6. That would have just been adding all 50 up and divided by 50. And it gave that the sigma for both of those is 3.3. So we have x bar 1 equals 8.6. X bar 2, which is the females, is 7.9. We have that sigma 1 is 3.3, and sigma 2 is also 3.3, and then we have both n's are 50. So n1 is 50 and n2 is 50. And again, on the test, I would take what's in these words and I would summarize it out in some sort of a table. So men's, women's, and then I'd have it, sorted out. Whoops, I did not label that right. Hold on a second. Let me redo that. Okay, let me try that again. This is men's, and this is women's, and then we would have them in a table. So after the problem, it would be, give it in a table where it's kind of summarized out so you can find things easier. Okay, so now let's look at our, and you don't have to give this table. This table will be given to you. Okay, so on the exam, there'll be a table given that kind of summarizes everything. All right, so now we're going to go to our formula. Z equals x bar 1 minus x bar 2 minus mu1 minus mu2 all over the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. In this case, x bar 1 and x bar 2 are 8.6 and 7.9. Like we said, mu1 and mu2, we're always assuming they're equal so that when we subtract them, we just get 0, so we don't have to do that. Go to the bottom, we have square root of sigma 1, which was 3.3 squared. I mean, we're squaring it because it has it in the formula. And then n1 is 35, and then same thing here. Sigma 2 was 3.3, and I'm sorry, it's not 35. That was from our last one. It's 50. Okay, so our sample sizes are 50 for both groups. If we calculate that out, that should come out to be, and give that a try on your calculator, type that in and make sure you can get it to work out properly. It should come out to be about 1.06. Let me calculate that really quick. So the top, of course, let me just do an intermediate step. If you're trying to make sure that you can get this on your calculator properly, the top would be 0.7, and then the bottom should come out to be 3.3 squared. And then if we do the square root of that, the bottom should come out to be about it comes out to be exactly 0.66. So then when we divide 7 divided by 0.66, we get, what do we say, 1.06. Okay, I'm going to take away the approximately equals because at this point, actually, this came out to be exactly 0.7 divided by 0.66. But then when we divide that, it comes out to be about 1.06. Okay. Oh, and I got ahead of myself here. We didn't do the, they did the p-value method, and we're just doing the traditional method. So we should have done our, critical values first, or critical region. So this would be step 1. What I did here would actually be step 3. What I should have done first for step 2 is figured out our critical region. So our critical region would have been, since we have alpha is 0.10, and we are doing a z-test because we were given the sigmas, then we're going to pull up our chart, and we know it's one tail because we are talking about greater than. So we only have a shaded region on this side. So we know it's a one tail, right, and we know it's a z-test, so we're going to be all the way at the bottom, but we have to have one tail 0.10, then go all the way to the bottom, and we get this 1.282. Okay. So we're going to reject if this is over 1.282, which it's not. Again, I should have done this first and then done the calculation, but I'm not going to go back and redo it. So this comes out here. It's not as high as 1.28. It's like, about in here. So we're not in the reject region. So our decision is we will not reject the null hypothesis. Do not reject the null hypothesis. Again, don't worry about this. This is p-value method. We're not doing that. So make the decision. Do not reject the null hypothesis, which means there is not enough evidence to support the claim. If we do not reject, that means there is not enough evidence. So, not reject. We always say not enough evidence. And if we do reject, that means there is enough evidence. So the last thing out of this section that is on confidence intervals, or not confidence intervals, hypothesis testing for the difference between two means when you have the population standard deviation, they talk about doing confidence intervals. But again, we are not required to do this. We're not going to do this. So don't worry about anything with confidence intervals. If for some reason you see something in the homework for Chapter 9 that talks about confidence intervals, by all means let me know right away, because we're not doing that. So now, in our very last example for hypothesis testing, we are going to look at testing the difference between two means using the t-test. I think I said at the beginning that I might not do one of these, but I decided to go ahead and do it. In the new edition, this is actually 9.3, and you will see full problems in your homework. Or you could see a couple problems in your homework. So in this case, everything is the same except for the fact that we're not going to be given the population standard deviation. We're only going to be given the S. And so in the formula we have S's. And then because we only have the S's, we have to do degrees of freedom on the chart. Okay, everything else is just the same. So in this case, a researcher wishes to see if the average weights of newborn male infants are different from the average weights of newborn female infants. So she selects a random sample of 10 males and finds that their average is 7 pounds 11 ounces with a standard deviation. Notice here, standard deviation of the sample is 8 ounces. Okay, standard deviation of the sample means it's an S, not a sigma. She selects a random sample of 8 females, finds their mean is 7 pounds 4 ounces with their standard deviation of the sample as 5 ounces. Can it be concluded that the mean weight of the males is different from the mean weight of the females? So let's make our table, which again, I'll give you this on the test. If you think of the male babies as the first group and then the female babies as the second group, Then you would have your average for the males, your X bar 1, and your average for the females, X bar 2. And we want to do this in ounces. It's a lot easier. So instead of 7 pounds, 11 ounces, remember there's 16 pounds in an ounce. So this would be 7 times 16 and then plus the extra 11 ounces. So what is that? 70 and 42 and then plus 11. So the 7 times 16 is 112 plus 11, so you get a total of 123 ounces. So male average is 123 ounces. For females, 7 pounds 4 ounces. So again, that's 7 times 16 is 112 plus the 4 ounces. I'll do it up here. So 7 times 16 plus the 4 ounces. 7 times 16 is still 112. Plus 4, you get an average weight of 116 for this sample. Pretty small samples, though. We only have 8 female infants and 10 male infants. Those are pretty small sample sizes. Okay, the S sub 1 is, get rid of some of this junk. Well, actually, it's kind of hard to erase on this. So S sub 1, standard deviation of the sample is 8 ounces. S sub 2 for the females, it was 5 ounces. And then the sample sizes in this case are actually different. The sample size for the males was 10, and the sample size for the females was only 8. So they had 10 male babies and only 8 female babies. Okay, so now our null hypothesis is that, as always, mu1 equals mu2. That the two groups are actually just babies is our population, and the population of males and the population of females doesn't really differ. They're just really from the same population. Our alternative hypothesis, in this case, it says that the mean weight of the males is different from. So that would be a not equals. For 2, we're going to go ahead and do our critical region. It's a 2-tail. We have an alpha as 0.05. And in this case, since we're only given S, we're going to have to do a t-test, which means we're going to have to do degrees of freedom. Now, I wanted to make sure to do this one. That's the way I kind of changed my mind on whether to do one of these or not, is I really want to point out that when the sample sizes are different and you have to do degrees of freedom, that can be a little bit confusing. Do I use the 10 and say the degrees of freedom is 9, or do I use the 8 and say the degrees of freedom is 7? I've also had students suggest, well, maybe should we average them? The average of 10 and 8 is 9, and so we do a degrees of freedom of 8. I mean, those are all reasonable ideas, and the answer to that is we can only consider our study as good as our smallest sample. Remember, bigger samples are better. So in this case, we're going to have to go with the smaller one as our degrees of freedom because, again, our study is only as good as that smallest sample. So we're going to use this one because it's smaller and use degrees of freedom of 7. So alpha 0.05, 2 tails, degrees of freedom 7. So degrees of freedom, 2 tails, 0.05, degrees of freedom 7 is right here. We get 2.365. So negative 2.365 and positive 2.365. And if we're going to reject if we're in these shaded areas. So these are our rejection regions. So now we're going to do our calculations. Zoom out a little bit here. Won't let me do anything between those. Okay, so I'll zoom back in. We'll squeeze it in. Okay, so we're going to use our t, it's the same calculation as before. I'm just going to use s's instead of sigmas. So difference between our samples, x1 minus x2, over the square root of s squared over n1 plus s2 squared over n2. In this case, x1 and x2 are those averages, the 123 and 116. Our s's are the 8 and 5. So 8 squared and 5 squared. And then our sample sizes were 10 and 8. On the top here, 123 minus 116 would give us 7. And then if we calculate the bottom, 8 squared divided by 10 plus 5 squared divided by 8, I get 9.525, but then I want to do the square root of that. And so it's about 3.09. And when I divide that, I get my t to be about 2.27. So where's that fall? Well, if I take this number and I compare it to what I had up here, 2.27, oops, I went the wrong direction. It's actually over here. So 2.27 is a little bit short of 2.365. So 2.365 is higher, so my number is not in the rejection region. Let me draw that a little better. I don't like the way that looks a little sloppy here. So 2.27, if I compare that to the rejection region, that's like in this area. It's not quite up into the reject region. So our conclusion is that we, where did it go? I have it here somewhere. There it is. So there is not enough evidence to support we do not reject, and there is not enough evidence. So since this is not in the reject region, or the critical region, we do not reject the null hypothesis because we're not in the critical region, and that means there is not enough evidence to support the claim that the average weights between the male infants and the female infants is different. We can just assume that they come from a large population of newborn babies. We don't have to think of them as two separate populations. And that's it for Chapter 9. So Chapter 9, you'll see one problem on the final from Chapter 9. Don't forget when you're reviewing for the final to go back and use the review materials in D2L. There's a review for the final, there's Zooms, there's review videos that I did live with classes. There's all kinds of resources. You can't just assume, oh, I've done all my homework, I'm ready for the test. Make sure you take time to review and study for your final exam. That's why you don't have anything due that week. The final exam isn't due till the end of the week. So make sure that you do that, and have hope you have a wonderfully successful final exam. And that concludes our hypothesis testing.